end behavior today. The end behavior, like I said in Algebra 2, you learned about how functions, they rise or fall to the left, they rise or fall to the right. So you're looking at the direction of the arrows, the way the arrows are pointing. And so the end behavior of a function describes how a function behaves as it moves infinitely to the right and to the left. So as your graph, when you see a picture of a graph, it stops at some point. You cannot have a picture on a piece of paper that goes on thing, and I might pull it up if we have time. But when talking about end behavior, if you look at a graph on Desmos, you just keep scrolling and scrolling and scrolling, and it helps you visualize that line keeps going forever and ever and ever and ever and ever. And so that's what we're looking at today. So in other words, the end behavior is what happens to the endpoints. I'm not sure what was supposed to be in that blank. What happens to the endpoints or the ends or the arrows as x increases or decreases forever and ever. So as x increases, that's going to the right. When you go to the right, those x values get bigger and bigger and bigger and bigger until eventually we just say it hits infinity. To the left, your x is decreasing. It's going negative to negative infinity. So for this, we are going to use what's called limit notation. You've never seen or heard of limits before. Actually, in AP Calculus, right now, I was in there one day, and they were doing stuff with limits. For right now, the only thing that we're going to talk about with limits is the end behavior. So what we're talking about a limit as like the graph gets closer and closer and closer to some point. That's just kind of the idea of a limit. But when you think about it in terms of end behavior, when you see the limit, so when you see, we're talking about end behavior, the limit, we say this, the limit as x approaches, the arrow we say approaches, negative infinity. So the limit as x approaches negative infinity is how I would read that. We're talking about, so as x goes to negative infinity, that's the left. If you think about a number line, your x values, negative infinity goes from like -1 to -2 to -100 to -1000. That's on the left. Okay. So this is the left side of the graph. The values are decreasing. So as you decrease, you're going up, we equal to this is what you have arrows are pointing, the y values are getting bigger. On a graph, up It's going to be kind of the same thing with the right in behavior. Infinity. On the right side. Okay. Increase. On just what that means bigger. We're saying this is where we stop. Without bound. They decreasing, we put negative infinity. So let's look at an actual example. Here you have a graph. As a verbal, and then we're going to turn it into the limit. So as x increases or decreases on the left, what's x doing? On 3.1 left, -4. It's smaller. So as x, your left side, when we're talking about the left side, use increase. Decreases on the left side. So the left side of the graph, x decreases. I don't know why. Limit as x approaches on the left side, x is getting smaller, so it's going to negative infinity. So the limit as x approaches negative infinity of, we'll just call this f of x, equals they're increasing, so they go to positive infinity. So I would say the limit as x approaches negative infinity, all that means is what's happening as my x's go farther and farther and farther to the left, what's happening to my y's? They're getting bigger and bigger and bigger. Okay? So infinity. Now on the right side, so right, we would say as x increases, okay, so as I move to the right, my y's are going down. So my y decreases. as x increases, as I go to the right, my y's go down, which is decrease. So I would say the limit as x approaches infinity. So as x goes to infinity, that means x is getting bigger. And then we put f of x there because we're talking about that graph, which I'm calling f of x. Like in calculus, what they're doing right now is they actually have an equation that they write there. We're looking at graphs right now. So the limit as x approaches infinity on the right of the graph, what's happening to the y's? They're going down, so I put equals negative infinity. Okay. So right here, that's what the y's are doing. So whenever you put equals, you're telling what's happening to the y values. I'm going to do the same thing here. So verbally, when we're talking about the left side, so I would say as x on the left, what's happening to your x's? Left, x's go down. So as x decreases, y, all right, are my arrows pointing up or are they pointing down? Up. So y increases. So as x decreases to the left, y goes up. So the left side pointing up. X decreases to the left. Y increases up. So as a limit, I would say the limit as x approaches negative infinity. So we're talking about the behavior as x is getting smaller. X goes negative, x gets smaller, of my graph, which we'll just call f of x, equals, so this part right here, you're always going to have this. When you're talking about the left side, it's always going to look like this. What it's equal to is telling us, all right, is it pointing up or down? So it's going to be equal to what? Positive or negative infinity? Positive, because it's pointing up. So positive infinity.
So does the one that the x points to, that depends on if it's increasing or decreasing?
Right. So if we're talking about the left side, it's all, your x's always decrease on the left. So when you're talking about the left side, it's always going to be this. X approaches negative infinity. That right there specifically means left. So you're always going to have that for left. This right here is going to change based on if it's going up or down. If your arrow is pointing up or if your arrow is pointing down. So when you see as x approaches negative infinity, that means the left side. When it's equal to infinity, that means on the left side, your arrow points up. So the right side, so as x increases, you're always going to have that. X increases specifically means right side. Okay. Is my arrows pointing up or down on the right side? Up. So y increases. So the limit as x approaches infinity. When you see x approaches infinity, that means we're talking about the right side of f of x equals. So since my arrow on the right is pointing up, again, I'm going to put a positive infinity. So if I just ask you, state or write the end behavior, you're going to have both of these. You'll always have both. You'll always have something that's happening on the left, something that's happening on the right. So here, I'm doing it backwards. I'm giving you the end behavior. You're going to sketch a graph. And every one of us could have a different looking graph. So here, as x approaches negative infinity, I'm talking about which side? The left or the right? The left. Okay. So on the left side, it's equal to negative infinity. So that means my arrow is going to point how? Down. So on the left side, my arrow is going to point down. As x approaches infinity, that's talking about the right side, my arrow is going to point down. So both sides are down. It doesn't matter how many humps and max and mins you have in between, as long as, right, that would be an example. You could simply just have an upside down parabola. That would work. But both sides, the arrows point down. So number 4, the limit as x approaches negative infinity. So again, here we're talking about the left side. My arrow points down, negative infinity. But on the right side, my arrow points up. So draw an example like that. That is one example. I could go look at every one of your papers and you could have something different, but it technically could still be right. As long as on the left side your arrow points down, right side it points up. That's all we're focusing on. Now, if I don't give you a graph, if I just give you the equation, you can still determine the end behavior. We did this in Algebra 2. That end behavior depends on two things. It depends on the degree and the leading coefficient. If you have, so your degree, we're looking at if it's an even number or an odd number. Be careful, we're not talking about even and odd in the sense that we did yesterday. If the degree is an even number, if it's an even number, even degree, your arrows point in the same direction. They'll either both point up or they'll both point down. So x squared, x to the 4th, x to the 6th, arrows point up or both point down. If it's an odd degree, they go in different directions. So one will go up and down. Okay. And whether they point up or down depends on if you have a negative in the front or not. So let's start with the even degrees. So they're both the same. If you have a even degree, so x to the 4th, x to the 6th, x squared, x to the 10th, and you have a positive number in the front, they're both going to point up. We did this exact same chart in Algebra 2. If it's even but you have a negative in the front, they both point down. Now the ones that are odd degree, so those arrows point in different directions. So you'll have one positive and one negative infinity in your limit. Okay. So on an odd degree, it's down then up. And then a negative leading coefficient would be up then down. And so the kind of the way I think about that is I think of x cubed. A positive x cubed looks like that. And so I can kind of base off of this one. A positive x cubed is down and then up. So I know that if I do a negative x cubed, it would be opposite. If you can kind of remember what x cubed looks like. Just the very original x cubed. Same thing for x squared. I know an x squared, a normal parabola, is a U shape. So it's a positive x squared, they both point up. So a negative x squared, they would both point down. And that helps me remember. Okay. So these first 6, okay, all we're going to do is look at the degree and the leading coefficient, and we're just going to draw the arrows. So for these first 6, just get used to drawing the arrows. We're not going to write limit notation on these 6. Okay. So degree, is it even or odd? What? Odd, right? The 5, my degree is 5, which is an odd number. My leading coefficient, that means the number in the front. Positive or negative? Positive. All right. So an odd degree and a positive leading coefficient. See if you can remember without flipping back in your paper. Just you're going to draw either an up or down arrow. So an odd degree, positive leading coefficient. It's like this. If it's just asking you about end behavior, you're not going to get a calculator on the test, on the AP exam. Like I could give you this and ask for the limit, your end behavior. So I don't want you to get in the habit of just putting it in the calculator and looking at the graph. Okay. Get used to memorizing. I will add those rules onto the Quizlet. Okay. All right. Number 6, degree. Even or odd? It's for even or odd? Even. Oh, too quiet. Which means my arrows are going to point in the same direction. And then my leading coefficient, positive or negative? Positive. So same direction, positive, they both point up. Oh man, I just realized number 9 and 10 are the same, and 15 and 16 are the same. Oh well. All right, so when you have x plus 3 to the 6th, you're not going to need to multiply that all out. That would be a lot of work. But all we care about is your overall degree, which is going to be a 6. Okay, so your degree is even. Your leading coefficient is going to be negative because of this negative in the front. So both of your arrows would point in the same direction because it's negative. Both point down. Okay. So number 8, degree. What is your degree? It's 5. It's just not, which is odd. Your degree is your largest exponent. It's not necessarily the first exponent. It's the largest exponent. And your leading coefficient, it's not always necessarily the one that's in the very front. It's always the sign that's with your highest exponent. So in this case, it would be negative. Okay. Technically, that equation should be rewritten. You really want to write it to where it would be negative x to the 5th plus 3. Okay. But obviously that was put there to trick you. So odd degree, but negative leading coefficient would be up then down. I really messed up because this one is really the same. It has a negative x to the 5th. I think I probably like copied and pasted and then didn't fix it. So this would be the same. 9 and 10 would also be an odd degree with a negative leading coefficient because my degree is 5. So you look at the sign in front of that specific term. So up, then down. So now, and 10 is the exact same. I gave you the exact same equations. We're going to redo it, but do it in limit, write our limits. Okay. So for the left side, if it's a left side, it's always the limit as x approaches negative infinity. You always, always, always write that for the left side. And then we're of f of x. I didn't leave myself enough room, really. Equals. So the 4x to the 5th, on the left side, we put that the arrow points down. So I'm going to put equals negative infinity. And then the right side, the limit as x approaches positive infinity. That's talking about the right side of f of x. What did we say about the arrow on the right side? Points up. So we put a positive infinity. So the 1/2 x to the 4th that we did here in number 6. When I'm talking about the left side, I'm going to put limit as x approaches negative infinity of f of x. If I'd put g of x equals, I'd put g of x there. You could also write 1/2 x to the 4th there as well. That's another way that it can be written. Equals. So that's the left side pointing up, positive infinity. Okay. And I've got my right side. It's pointing up. I'm going to put positive infinity. Another way that you can kind of see this, if I plug in numbers for x, if I plug in 10, well, if I'm doing negative infinity, if I plug in negative 10, negative 100, negative 1,000, negative 10,000, and I keep plugging in those numbers for x, my y values are going to get bigger and bigger and bigger, and they're always going to get bigger and bigger. All right, if I plug in positive 10, positive 100, positive 1,000, my numbers are going to get bigger, bigger, bigger. Okay, that's another way to see it. If you don't have a calculator, it makes it a little harder. You just need to remember those rules. All right, so go ahead and try 13, 14, and 15. You can leave 16 off. It's the exact same. Alright, here's what you should have for 13, 14, and 15.